In this video, I will apply the seamless object-oriented requirements approach to a realistic requirements document that describes the behavior of a software controller for train pantograph. Train pantograph is this device that takes energy from the wires and moves it to the train. And more specifically, I will use one of the requirements that says if external power supply is active in the train, then no pantograph in the train shall be selected. The seamless approach relies on a library of requirement patterns identified by Matthew Dwyer and his colleagues around 20 years ago and hosted on a website that you can see on the screen. These requirement patterns are expressed in several mathematical formalisms, including linear temporal logic that you can see on the screen. And some of the patterns are really complicated. And what I did, I have encoded these patterns in the form of object-oriented classes in Eiffel programming language. And I brought the complexity of this formal semantics into these patterns so that the practitioners who will apply these patterns will not see these complications. They will just map their requirements to individual components of these patterns, which are the events on which these patterns operate, and just use this semantics as it is in the original patterns. Okay, let's take a concrete example. The example says something that falls into the absence after Q pattern. This pattern is encoded in the following form. In linear temporal logic, it says that it is always the case that when we observe Q, we will never observe P since that point. How to apply this pattern to our example? We go to the library of patterns, find the absence after class, and use it in the following way. So this class is a generic class that depends on 3 generic types. I'm not going to explain the details here, but as you can see, the pattern is pretty complicated. Luckily, it exists and it's already implemented. You don't have to implement it again, and you can use it for specifying actual requirements. So how to do that? We declare class, I decided to call it rec1 to reflect the fact that I'm working with the first requirement in the document. And this requirement class inherits from this pattern class, providing all the necessary generic parameters. The first one is the candidate implementation of the pantograph controller. The second one and the third one are the classes that encode the events about which the pattern talks, namely Q and P. Now, having this formalization, we need to make sure that the formalization reflects the original meaning. And we can actually run this application and it will output the generated natural language representation of the requirement. Let's copy it into the original document and compare with the initial meaning. It says in pantograph controller, external power supply is active is false after no pantograph selected in the train. It seems that the formalization reverses the events. It should be the other way around. We say that no pantograph should be selected in the train after the external power supply is active. So we go back to the requirement class and swap the classes corresponding to these events, run it again, and copy the new representation to the document. Now it says no pantograph selected in the train is false after external power supply is active. Now the sequence of the events is correct, but we can see a double negation here. No pantograph selected is false. There was no double negation in the original requirement, and we need to remove this no. So we go to the formalization, and first we rename the class encoding this condition, and then we go inside in this class, and we also need to remove the not operator that actually formalizes this condition. So here I'm showing you a little bit of details behind the scene. Now we run it again. Now it says pantograph selected in the train is false after external power supply is active. So now this seems to be reflecting the original meaning, and we can proceed with verifying the requirement. By the way, this generation of the natural language representation is encoded inside these patterns. It is basically here. How to verify this requirement against the candidate implementation? There is a tool called autotest.